part now is going to be a new part of our courses. We have seen like a traditional, like a really fundamental way of thinking, divide and conquer, dynamic programming, and another nice way of analysis, which is called amortized analysis, right? So that's like really kind of maybe like 50 year, starting from that. Now we're gonna look at randomization, how randomization helps in computer science, and that like started like a bit later, but something like in the 80s, so like 40 years ago. But you'll see throughout the course from now on, like you'll see like again and again how randomization helps in computation. Like it's just gonna occur throughout the course from now, okay? And let me start with this quiz, like just to illustrate that randomization help. So suppose that you have an array here of size n, and I promised you that there are two cases possible. The first case is that most of the cell is like a small fraction of cells is 0, and most 90% of the cells are 1s. Okay, that's the first case. And another case is just the flip of that. That is 90% of the cells are 0, and the rest are 1s. Like just 10% of the fraction, 10% of the cells. Okay, so now what would be the fastest deterministic way to figure out which case it is? Yeah, go ahead.
I think you could take 2n plus 1 arbitrary elements, and whichever, like, you're going to have either zeros or ones. One of them is going to have an amount that exceeds n, and that one is the 9 out of 10 one, and the other one is the 1 out of 10.
Good. So guys said that just look at basically look at 2n over 10 plus 1 cell, right? And then return the majority, and that's correct. Yeah, because you know that if it's the first case, then you know that the majority must be 1, because there are just n over 10 many zeros. So that's correct. And okay, so that you don't need to look throughout the whole array. You just need to look at 20% of the array. Still linear time. Okay. So that's correct. And you can convince yourself that if you look at less than this many cells, it's not gonna work. Because as long as you look at less than, let's say you look at n over 10 cells, then you actually don't know which case it is. It might be the first case, but somehow all the cells that you look at are all 0. Okay, so that's this is the best you can do for deterministic algorithm. You need linear time. Okay. So yeah. So basically, guys, solve this exercise. Yeah. You need this many cells. So now, if I ask you, what about a randomized algorithm? Let's say I want to be correct with 90% probability. How many queries do I need? Scott?
If you just take 1 and then you just say whichever one you got is the more common one, you're going to be correct 90% of the time.
Yeah, exactly. Just do 1 query and return the value of your random cell. Because you know that if it's the first case, then if you choose a random cell, then with 90%, you're gonna get 1. In the second case, with 90%, you're gonna get 0. So okay, so here you just need 1 instead of linear. From linear time, you can reduce it to just 1. So that's good. So this is like just a toy example that, okay, sometimes like randomness really help you, and we'll see more and more example when it helps. Okay, but to do that, we will need to. I need to review some of the basics that you need throughout this class. Okay, and then we're gonna see that. Okay. We're gonna see how random function is useful, but actually a completely random function is not efficient. And then we're gonna see that, okay, that is actually like not a completely random function, but it's efficient. Like there exists an efficient hashing family or random functions, family of random functions that not completely random, but behave randomly and is good enough for you. And then we'll see some application to data structure. Okay, so let's start with the basics. Okay. So I will just review very quickly the basic concepts, right, in probability. And the running example is gonna be imagine that you have you're gonna roll 2 dice. Okay. So what is probability space? It's a set of all possible outcomes. Okay. So in this case, the possible outcomes are either is the first row is 1, the first die is 1, give you 1, another one 1, 1, 2, 1, 3, and so on. Like there are basically 36 many outcomes here. Okay. What's the event? Event is just a subset of probability space, like a bunch of outcomes. That's the event. For example, when the sum of the 2 dice is 7, that can happen when the first die is 1, the second die is 6, the first die is 2, the second die is 5, and so on. Okay. So it's just a set of possible outcomes that is in this, that satisfy this condition. So that's event. Event can be both dice roll to even numbers, something like that. Okay. Probability distribution. What is this? It's just like assignment from all outcome to 0, 1, so that the sum of it is 1. In this case, the probability distribution of all the outcomes are uniform. They are all the same, 1/36. Okay. And probability of an event is just the sum of probability of all the outcome in the event. Okay. So, for example, the probability that the sum of 2 dice is 7 is this much, because there are basically 6 events, 6 outcomes here that is in this event, right? And each of the outcome happen with 1/36. So there are 6 events, so 6 outcomes here. So it's sum to 6/36. Okay. Random variables, just any function that map an outcome to some real number. Okay, can be negative, can be positive. For example, if I say x is a sum of 2 dice, then given this outcome, x is 6. Given this outcome, x is 3. Okay. Basic thing. Another thing that the term that I will use, okay, this is important now, but I said if y indicates if both dice roll to even, here it means that if the outcome satisfy this event, then y is going to be 1. Otherwise, y is 0. Okay. This is the term that I will use in this class. Like y is an indicator of this event. So if you have the event, then y is 1, otherwise is 0. Okay. So and now let's recall what's independence. Well, the two events E1 and E2 are independent, and I will denote with this notation. They are independent if the probability that E1 and E2 happen at the same time is just the probability of E1 and times the probability of E2. Okay. For example, the event that the first dice rolls even and the second dice roll odd. These are independent. Okay. They happen with probability like 1/6 times 1/6. No. 1/2 times 1/2. Okay. But these two events are not independent. Okay. So this is like a kind of the formal definition, but I think we kind of know what it means to like for the two things to be independent. Like this is really intuitive, but it can be formalized in this way. Okay. And now, what about two random variables? We said that two random variables are independent, which I denote in the same way. If for all outcome x and y, for all value of x and y, like the event that x equals to x and the event that y equals to y, these two events are independent for all x and y. Okay. And you observe that this is just true if and only if this is the case. And this makes even more sense like intuitively for human. It means what? It means that the probability that x equals to x, given that you know something about y, it's just the probability that x equals to x. So that is like y, like knowing something about y doesn't affect your knowledge about x at all. Okay, that's why they are independent. Like so, this formalization really captures our intuition. Okay. And so the value of the first dice and the value of the second dice are independent, for example. Okay. And now, what about expected value or mean of some random variable x? This is simply the average value of x. When you weight, it's average weighted by the probability, right? So it's like an average value of x overall outcome weighted by the probability. Okay. And another way to write this expected value is just like a sum over all value, the probability that of the event that x equals to k and times k is the same thing. Okay. And there is one really important, simple but super important equality, which is just the linearity of expectation. Expectation of x plus y is expectation of x plus expectation of y. So this is like kind of, you can see this from just kind of from this definition. You can prove this easily. And this always hold. Even if x and y are not independent, even if they are related, it's always true. But when x is independent from y, you know more. You know that like expectation of x times y is also the expectation of x times the expectation of y. Okay. And you know that like this thing is true only if x and y are independent. If they are not, this might not be true. For example, think like x as like a random coin, like can be 0 or 1, and then I define y to be like a flip bit of x.
15 minutes long?
Okay. So you see that both expectation of x and expectation of y is just half, right? But the expectation of its product is always 0. because one of them will always be 0. So this is just not true when x and y are related. Okay. And a next concept is a variance. What is variance? It's like an expected square deviation from the mean, which is here. Okay. This one.
No, but it's not even just that.
And okay, you can write it in this way too. Just expand it, and you can see that it can be written in this way.
I was thinking a little
Okay.
the average value.
So now, when x and y are independent, you can prove also that the variance is linear as well. And again, this is not true. Like for expectation, this is always true. For variance, this is true only when the two variables are independent. Okay. And how to prove this? Well, it's just just expand the definition, right? And the variant of x plus y is just this minus this thing. Follow from here, and expand the term. This part give you here, and this part give you here, and then this thing gonna cancel out. Why? Because now we use that they are independent, and when you cancel out, you rearrange the term, and you get that you get a variant of x plus variant of y. Just some calculation, and you can confirm this. Nothing you don't need to go through this carefully right now, but convince yourself at home that it's true. Okay, so that's a really quick review of all the basic concepts in probability. Hopefully you have seen all of this before in some class, right? Okay, good. And now next is a basic bounds, right? That we will use in this class. First is just union bound. That is, for any two events, the probability that A or B happen is the probability of A plus the probability of B. Okay. And the proof is just from this picture, right? Yeah. The probability that you get A or B is probability of A plus at most probability of B. This is gonna be equal. This is gonna be equal if A and B are disjoint even. But otherwise, if they have intersection, you just get inequality. Okay. And in general, if there are n many events, then the probability that one of them occurs is just at most a sum of each probability. Okay, now just some quiz for you. Suppose that there are n processes, okay? And I said that each of them fail with probability at most, let's say at most 1 over n squared. And this process might be related, okay? Can you tell me, can you know about the probability that all processes succeed? Can you give me some lower bound of this quickly? How would you do this?
Using union bound?
Yeah, how?
Plus 1 over.
Yep.
I don't know if I'm right, but if each fails with a probability of 1 over n squared, it means they succeed with the probability of n squared minus 1 over n squared. Or sorry,
One minus one.
yeah.
Okay, succeed with like this probability 1 minus 1 over n squared.
Yeah.
Okay.
Which is n squared minus 1 divided by n squared.
Yeah.
But yeah, so if the probability that they all succeed, I guess you could kind of use union bound and multiply by n for adding each one of them n times for all processes to succeed. And you get, I guess, n minus 1 over n.
Like
N squared.
look at this. Yeah, I that's good suggestion, but it's not gonna work yet because of this. This is kind of basically close to 1 already, and if you like add this thing up n times, this is already more than 1. So like when the probability is more than 1, it doesn't give you anything. Okay,
I think it's all to the power of n,
all to the power of n.
because there are n processes. So that's the chance of success of one process, and you need to have an n time.
Cannot do that because they are not independent. Yeah, John.
We didn't. This union bound gives an upper bound and we're asked for a lower bound. So we sum the probability of all processes and that gives us n times 1 over n squared, so that's 1 over n. And that's the upper bound for the probability that one fails. The probability that none fail is 1 minus that.
Very good. Thanks, John. So, like the trick is here. Like you see that like this is about like a for all event, and union bound is really about like if there exists something, right? So if you try to use union bound, you need to like talk about exist, not for all.
Yeah.
And so the trick is okay. You analyze the probability that there exists some process that fails. That's just a flip of for all succeed, right? Negation of for all succeed. So analyze this. And now with this, you can apply union bound. This probability that exists some process I that fail is just sum of for all I, the process I fail. And this thing is just at most 1 over n squared. And there are n processes. And this you can do, like, know that this you can do for even if they are related. Okay? And here you get n over n squared. So this is the probability that all some process fail is 1 over n. So all succeed is at least like 1 minus 1 over n. Okay, good. So this kind of trick you use quite a lot, right? You will need to use at least in some homework for sure. Okay, so now next part I'm gonna talk about concentration inequalities. Okay, so why do we look at concentration inequality? Because when you have random variables, like the easiest way, the simplest way to describe it is to look at the expectation. That's like a simplest description of the random variables. But like many times you want to say that that random variable is close to its expectation. That's when you need concentration inequality. Okay. How to say that, like what really happened is not too far from its expectation with like with good probability. Okay. And have all of you seen Markov inequality? How about Chebyshev? Good. Then I just remind you. Okay. So Markov inequality apply for any non-negative, right? Only non-negative random variables, and basically it says that the probability that x is gonna be too big, like a t times its expectation, that is like a 1 over t. Okay. And that is the same as like saying that like just replace t by this one, x is greater than t with this probability at most. if you don't recall the proof, I recommend look at this lecture note. I put a link there. For Chebyshev, okay. Chebyshev apply for any random variables, not just non-negative one. But it says something similar. It says that x deviate from its expectation by t. This event will happen with probably something like the variance of x over t squared. So the intuitive way to think about this too is that like here you get something like 1 over t. Here you get like a stronger bound t squared here. But here you need to be able to analyze the variance. Okay, so you need to know more information, not just the expectation. Okay, good. All right. So now these are like a basic things, but there are like really stronger concentration bound. And you can do this super strong concentration bound when you look at the sum of independent random things, random variables. Okay. For example, if you say that let xi be the indicator of the result when you toss a coin I. Okay. So xi is like it's uniform here. And let's say that x just count the number of heads from n tosses. So you know that like okay, expectation of x is just like our n over 2, simple. And okay, but if you look at the distribution, how x, like distribution of x, when there are 10 coins like this, when there are like more, it looks like more concentrated. When n grows and like grow more and more, it kind of get more and more concentrated. Like here it's just like, even when you focus on 0.4 and 0.6, it's just around the expectation here. Nothing here is 0, it's just like too small to see. So you see like this is really concentrated, and basically, yeah, the sum of independent things are really predictable, basically. And that's formalized by Chernoff bound, which I'm gonna say next. Okay. So Chernoff bound says this: if you have a bunch of random variables from 0 to 1 that are independent, and look at its sum, and let's say mu is a mean of x, then then you have this. You have that like x. Think of this as 0.1 maybe. Okay, lambda as 0.1. The probability that x deviate from the mean below the mean by like a 0.1 of the mean. That's basically like exponentially small, like something exponential. This is constant times the mean. Okay, so if you think of mu from last example, like n over 2, this is exponential in n. Okay. And this thing says like if lambda is 0.1, the probability that x deviate from the mean more than the mean by like a 0.1 of the mean, that's also like exponentially small. Okay. And you also have like a better bound for large deviation. Like basically it's the same thing here, but here like lambda now is like maybe more than 1, can be like 10, even like log n, something like that. Right. Here you get something exponential in mu as well, but the base of the exponential is now lambda. So not just e, like the base of exponential also like grow with lambda. Okay. Question about the interpretation of this Chernoff bound. Is this a thing that you have seen for this one? You have seen it too. Not okay. Not all. Okay. So yeah, like the point is like you see that it's just so strong. Like instead of getting like something like the bound which is like 1/t square like in Chebyshev and Markov, this is like exponentially small, right? So the probability that it just deviates from the mean is just so small. Okay. There are many proofs of this. So many proofs, like I use a bunch of algebra. Not so intuitive, but just this year there is like a new paper that published a new proof that is quite simple. It's not as sharp like this. Like you're gonna pay more in the constant, but if you want to see the proof, that like this is the proof that I like. So far, I don't like any proof because it's just a bunch of algebra and cannot really make sense of it. Okay. Good. If anyone want to read this, I can put it as a project too. It's a nice paper actually. Okay. So now you've seen like some concentration bound. Let's try to apply it in some scenario, which is balls and bins. Okay. So balls and bins are the process that is really classical in probably like a really classical probabilistic process, and we're gonna look at it a bit. Okay. Suppose that you have n balls and n bins. You have bins, like bins, n of them, and you have n balls. And then you throw each of the balls like to each bin randomly, uniformly, and independently. Right? For each ball, just throw in the random bin and do this repeat like independently for each ball. Okay. So and then I let like the load I to denote the number of balls on bin I. Okay. So what we good. Maybe I ask you this first. What is the expectation of load I? Anyone? Yeah.
1.
1. Why is that?
Because with each throw, probability of it landing in a given bin is 1/n, and then we basically so we can define like our indicator variable as like xi is like 1/n, and then we just do sum of 1/n n times.
Yeah. So like how to analyze this, you can, for example, define like some indicator. Let's say Bij to indicate that ball J goes to bin I, right? And then you see that load I is just a sum of ball J, bin Ij. And then this is just sum of Bij. And then you can apply expected, like linearity of expectation, and you get here Bij. But this is just like the from the definition of indicator, right? This thing is just a probability that ball J goes to bin I. This thing. So this is like 1/n. So when you sum this thing, you get n times 1/n, which is 1. Okay. So the expected load for each bin is 1. Okay. But we're gonna look at something else. We're gonna look at, can you show that the maximum load is at most something with good probability? Okay. This is not about expected number, right? Not expected value. We want really to show that, okay, none of the bin have more than some bound m. with good probability. Okay. What's the best M that you can prove? That's our goal. And this is when a concentration bound really is good for you. Okay. So that's the goal for now. The goal is clear, right? And okay, let's try to do this. Well, if you want to prove that max load is at most M with 90%, the useful strategy is, again, max load is about for all statement, and usually it's easier to look at for each statement. What do I mean by that? Max load is this thing, right? It's about probability that for all I, load I is at most M. We want to prove this. But actually, it's easier to show something like this instead. Like for each I, load of I at what is the probability that load of I is at most M? We want to prove something like this instead. You see the difference, right? Here, this is about for all I. What's the event that is happened? And now instead, this is just easier thing. Just fix one I. What is the probability that this happened? It's just it's just such much simpler event to look at. Just one bin, not for all. Okay. How do you work with this? Well, we're gonna use union bound. Suppose that I can show that actually for each bin, the probability that load is more than M is 1/10n. If that's the case, then can you tell me quickly why are we done by union bound? Yeah, Scott.
Because then if some union bound will get the probability that, or we'll get for all I the probability that load I is greater than or equal to M is less than or equal to 1/10n times N. Which would just be less than or equal to 1/10, and then since that's the inverse of what we were trying to do.
Say again the probability of what?
Sorry, probability that there exists in I,
Good.
not for all I. Yeah,
Good.
I realized I said that wrong.
Yeah.
And then that's the inverse of probability for all I. So then
Exactly.
It's not the clearest.
So you see, when you want to apply union bound, just you have that the probability that the excess the load I such that this is more than M. That is just by union bound is a sum of this probability, and each of these is at most 1/10n, and that's going to be 1/10. So it means that for all I with 90%, they are at most M. Okay. So you're gonna use this trick again and again. So get used to it, right? Okay. Okay. So now we have that. Okay. With union bound, it allows you to just now look at one bin, not all bins. Okay. Now that's the goal now. Try to bound the probability that load I is more than M, and show that this is show the strong bound, 1/10n. Okay. And yeah, to give this a tails bound, to bound the concentration, we will basically compute the expectation of load I first, and you know that it's 1. We have seen this. So next is just try to show that it's concentrated, it's close to the expectation. And we have a bunch of choices of the bounds that we know how to apply. So let's try to apply Markov. Right, this is Markov bound. And then here we're gonna get in our case, we have that probably that load I more than M is just expectation of load I at most M. Okay, and this is 1. So we need to set if you want this to be like 1 over 10n, you need to set m to be what? 10n. So that seems useless, right? Like there are n balls, and so there's no ways that like a load I is gonna be more than 10n anyway. So that's basically useless. So Markov is not strong enough for this case. Okay. So let's try to use Chebyshev. Okay. So in this case, let's say that I write like a load L as the load I. Okay. So now if you want to apply Chebyshev, you want to prove that load L is at most m. To apply Chebyshev, then you see that like this is at most expectation of L deviate more than m minus 1. Okay. I just rewrite so that it looks like something to use that I can use Chebyshev.
So where did the -1 come from?
The expectation is 1. So like this thing asks about so this is 1, right? This is the event that L deviates from 1 by more than m minus 1. So if this happen, this must happen. But I also bound the like the event that L goes below 1 too. Okay, but I need to write it in this way so that I can apply like Chebyshev. Okay. And now this is like a variance of L times m minus 1 square. Okay. So you see like we used to have like a m, now we have m square, so it looks better. Okay. So now we just need to analyze variant. But so variant, variant of L is the sum of L is like a sum of indicator that bin like a ball J's go to bin I, right? So this is just here. Okay. Now I'm gonna use that is linear. Why can I use this? Because these random variables, like for all j, they are independent. Like each ball are independent from each other. Only then I can use linearity of variance, right? Otherwise, I cannot use it. Okay. And you actually can prove that the variant of this, like when this is like a 0, 1, then this is at most the expectation. Okay. And so this is like 1. So like when this is an indicator is like either 0 or 1, the variance is at most the expectation. And so sum of expectation is 1. Okay. So now it means what? This is 1. So if you want to set, if I set like a m to be now like something like root n plus 1, then you get, then this is gonna be like a 1 over 10n. Okay. So now this is something non-trivial, right? We get now that like by setting m to be this much, we get this one. So we conclude at the end that no, the maximum load is at most root n. That's good. So this is kind of non-trivial, but still far from being tight actually. Let's try to use something else, like a Chernoff bound. And Chernoff bound said this, for sum of independent 0, 1 random variables x, you can apply this one. Okay. And indeed, if you look at the load I is a sum of 0, 1 independent random variables, like the bij. For each j, they are independent. So it's you can apply Chernoff bound. Load I is a valid random variables to apply Chernoff bound. Not all of them, right? You need to be careful, but here we can. And now, okay, try to apply this one. So then I just try to rewrite it so that it looks like the same form here. Okay. And then I get the bound is m to the minus m, basically. Okay. And then if I just set, now instead of, if I want this to be less than 1 over 10n, I can just set m to be something like log n over log n. And you're gonna get it. How to see this? For example, if this is a 2 to the log m, not base, the base here is not m but 2, then you can see that when you set m to be log n, this is gonna be 1 over n. Right? Now the base of the exponent is m, so even log n over log n works too. Okay. So you see now the Chernoff bound is just so strong. Yeah. It gives you a exponentially better bound. Okay. So now you can conclude that with 90% probability, no bin will have more than log n over log n. So now instead of saying that with 90%, I want to talk about something called with high probability. And when we say high probability, this is actually a formal definition, not just some colloquial way to say things. So suppose that the problem size is n. If some event fail with probability 1 over n to the c for any c, if this is true for any 1 over polynomial of n, then we say that we succeed with high probability. That's what I mean in this course. Okay? And from the balls and bean experiment, actually you can say that max load is going to be at most this, not just with 90%, but with high probability. Okay. And the reason is just that for any c, you can choose a constant in the m, choose constant in the log of O of log n over log n here. Choose a constant so that when you apply Chernoff bound, you're gonna get this one. Okay. And so it means that the excess by union bound, this is the excess load that is too big with just one. We fail with just this probability for any c. Okay. Question about this? Yeah.
So can we only ever say we succeed with high probability if we have some sort of O of something, because then we basically can match the C.
Exactly. When we use some asymptotic a O of something, yeah, like you said. Okay. So that's basically kind of some review on how you use concentration bound. And now let's look at some application. Okay. Let's try to now go to now like come back to computer science. Okay. Let's look at the basic data structure like the dictionary. Okay. Where you have a maintenance set, you can insert, delete, look at predecessor or successor. Here you know that with balanced binary search tree, everything here can be done in log n time, and the space is just linear. Okay, that's good, but can we do better? That's the goal of today. We want to show that actually you can improve log n to constant with randomization. But we're going to do this in a restricted setting. That is, let's say I don't care about predecessor and successor. I just want to insert, delete, and check if like the element is in a set. Okay. And also we're gonna work with this model, bounded universe model. Okay. That is, all the elements or all the keys are in some number. You know, like the keys are fixed to be some number. Okay. From 0 to some u, where u is like a size of universe. And u here you should think of like maybe like it's like a 200 bits string, like URL or something. So u is actually like huge, right? It's much bigger than n, where n is the number of things in your dictionary. U is like huge, but it's still a number. Okay. Right. So this is already like useful. Yeah. Okay. Think of like you kind of store like a bunch of URL, for example, in your history of browser or something like that. Yeah. Okay. So there's one trivial implementation of this problem. Just allocate the array of size u and implement everything in a trivial way, like do it on the array. Here the operation would take constant time, but it would require you like use space. So that's just not acceptable. Like when u is like a 2 to the 200, that's too big. Yeah. Bigger than the size of universe, bigger than the number of atoms in the universe. So that's too big. Okay. So now now we're gonna use some randomization to get some improvement over binary search tree. And the idea is it's called hashing with chaining. Okay. And we're gonna assume random function. So note again, random function is gonna be useful for designing things, but it's not gonna be efficient yet. You're gonna see why. Okay. So what's the idea of this data structure? Well, if the size of the set is like n, suppose you know this, or you can approximate this, then let's try to allocate the array of size n. Okay. Allocate the array of size m when m is n. And now on each cell in the array, it contains the linked list. And we're going to assume that we have access to the completely random function h that map the universe to some cell in the memory in your array. Okay. So that is for anything in universe, any string x in universe. Well, h of x is a random number in M. Okay. And assume also that h can be evaluated fast in constant time. We're gonna remove this assumption later. But assuming this one, now there is like a supernatural way to implement the dictionary. So suppose I want to insert element x with the value val, then just append this value to the list at the random position that h map x to. If I delete, just reverse what I did. And if I want to look up for x, then just look at the list at the position of hx. Okay. So this here is an example. Like for each pairs, it just kind of go to the random place, and if they go to the same place, then they are like linked by the linked list. Okay. Is it clear? Okay. Super simple data structure. And now like the time to insert, delete query is just it's like for the key x is just like the size of the list at position hx plus the time to evaluate hx. Okay. For the red part here, I assume it's constant for now. But what about the black part? Okay. What's the size of this? Can you see any connection to balls and bins? Can you, any of you explain? Too clear? Scott, yeah, go ahead.
So if it's like mapping a function of size like u or cardinality size u, which is cardinality of u, to m, then we only have m things and we need to fit u into them, so it's going to be u over m in each array is like the size of the list.
Wait, like u is the size of universe, but there's going to be only n keys that we're going to store.
Yeah.
Okay.
So well, isn't it u over n, right? Each or like at each array we have
As if we added the entire universe.
well yeah, but we're talking about worst case, aren't we? Like the worst case size of the list would be u over n.
Like
So-
you're saying if we add at most.
So like you said that like the size
we're
of
saying we
this
only add n.
might be u over n, but that's not the case because u is a size of huge universe. We're gonna have like only n elements, and so okay, u size of universe, n number of keys, and m the size of array.
Oh, I see. So then it would be n over m.
Yeah,
Sorry, I thought I didn't realize I
right.
get the n definition.
So we basically kind of expect that the size of this thing should be something like m over m, n over m. In balls and bins terminology, like each key is like a ball. This is a bin. Each cell is a bin. Each key is thrown to like a random cell. So there's like the load of bin I is like the size of the list at bin at cell I. You see, it's just like the same scenario. Okay. So so the expected load for each bin is 1. It's actually 1 because we set m equals n for now. Okay. And we also have analyzed that the maximum load is going to be log n over log n with high probability. So it means what? So from balls and bins analysis, it seems like, okay, now, although the size of the universe is huge, u, the space that we're going to store is like m. We only allocate m cells, and that's like linear space. Okay. And expected time for each operation is the expected time for it's like a expected size of each of the list here, which is constant. So expected time is constant. Worst case time is going to be log n over log n, because that's like the maximum load that you pay. Seems great. Except that like we assume the random function, and that's actually really expensive. Let's see why. Okay. So we want to avoid it, but let's see why it's inefficient first. Okay. So if I have like let the set all, okay, be a family of all functions that map the universe to M. Okay. How many functions are there in the set all? Like how large is the set all? Well, it's gonna be M to the U, right? It's like you, for each choice of U, for each thing in the universe, it has M choice. So, like, if there are 2 guys in the universe, this would be M squared, but there are U many guys in the universe. So there are like M to the U, many functions. Okay. Among this, how many functions have this many bit of representation? Have this size bit representation? Well, it's gonna be like if you have like k bits of things, then k bits can represent only like 2 to the k many things. So if you have this many bits, then there are this many functions that can be represented using this many bits. And what is this? It's just like something like square root of M to the U, which is much less than M to the U, of course. So it means that, and how big is this thing? This is log of this is basically U log M. You see? It means what? It means that there are M to the U functions. Only few of them need can be represented in this much space, which is like a U log M. It means that most of these functions takes more than this much space. Okay, like U to the M minus this much minus this takes more than this much space. Okay. Okay, so it means that if you just choose a random function from the set of all functions, it's gonna take this many bits at least, which is like a U log M. But this space is just like as bad as like when you use like trivial array implementation, right? When you use array implementation, the trivial one, you take like a space of size U. It's like this many bits. So like just to represent some function that is completely random, it already takes you too much space. Okay. You see this?
Yep.
Like random function is just too, yeah.
Am I missing? Why is like the 1/2 required in this case?
Because without 1/2, you're not gonna get square root. Like if I put like a 1/10, then this is gonna be this thing to the 1/10. I just like put something so that this is much less than this thing. Yeah.
So does that mean theoretically like every function could be represented in log to M to the U space because that would result in M to the U?
Yeah. Every function can be represented in log of this much, but you see, it's just too big. It's just kind of useless. So the goal then is here. The goal is to define like some smaller family of functions, not all, but some better family H. Okay, and this family should be like this. When you sample a function from this smaller family, not all, but from the like good family H, then the function from this family takes more space, and it kind of behave as if it's random. That's the goal. Okay. Like we kind of want something that behave like random function, but still efficient. But what is the behavior of random function? Well, you can list a bunch, right? One is that, okay, for each element, it should like, for each element x, it should be mapped to like a number I uniformly. That's one. What else? Like small collision. If there are two different elements, then they map to the same place with probably like 1/m. This is true as well for random function. There are more things like pairwise independent, which says that for any different element, okay, then the probability that x is mapped to I and probability that y is mapped to j is 1/m squared. This is like all of this trivially certified by random function, but it's just not clear that some function might certify this without being like completely random, right? And you can talk about like a more general one called k-wise independent, which basically like pairwise independent but have k many terms. Can talk about k many different keys. Okay. So this is basically kind of the hierarchy of like behavior. A complete random function would be n-wise independent. That is what it means to be complete random actually. But like n-wise independent implies like n-1 wise independent implies k-wise independent implies 2-wise independent, and 2-wise independent implies these two actually. Okay. Like if you want this thing, it means you need complete random function, which is too inefficient. If you want just this thing maybe, then you can hope for something much more efficient. Yeah.
Right, so the distinction between k-wise and n-wise independent is that just k is just some value less than n.
Yeah. Right. Okay. So we're gonna just look at this one. Okay. I'm gonna show you like some family of functions that will satisfy this small collision, but you see that it's so much simpler to describe and evaluate. Okay, and that's called universal hashing families, okay, of a hashing family with small collision property. So we say that a family H that maps U to M has small collision property if for any x and y that are different, the probability that they map to the same place is at most 1/m. Okay. And people call this name universal. It's like a misleading name, but it's been in the literature for a long time. But so when you say universal, just think of small collision. Okay. And note again that this property of small collision is the property of a family, not about one particular function, right? Like when you sample from this family, sample a function from this family, it satisfies this one. It doesn't make sense to say that like just one function, one fixed function satisfies small collision property. It needs to be about like one family, like a set of functions. Okay. And okay, let me show you what is like one example of efficient and universal hashing family. Okay. So suppose that U is a prime. Okay. And I can define like HA to be like this. Like given any number x, I multiply it with A, and then I mod the prime, and then I mod with M, so that it maps to like universe of size M. Okay. And then I just define the family of functions to be all the h a for all a's range from 1 to p minus 1. So obviously, like, this is like so much simple to describe, right? Like for each function here, it takes O1 space, right? Because you just need to remember A. That's the only thing that describes H. And to evaluate H, it takes constant time too.
And so like capital H, the family of functions is parameterized just by the prime number P?
Yeah, this is like parameterized by P and M actually. Because you mod P and mod M here. Okay. Now I just need to say that, okay, H has a small collision. Okay. The family has small collision. It means that, like, for any different x and y, let's say x is more than y, for any different x and y, I need to talk about different elements, right? Because if they are the same number, they must map to the same place, for sure. But I need to show that for different x and y, I need to show that when H is sampled from the family, that is, I choose A randomly, then this they collide with small probability. Okay. And for now, I will not show the proof. The proof is actually like a simple math, but I would need to skip for now. Okay. Let's see if I have time, but skip it for now. Okay. Just do some simple math, and you can prove this. Okay. But my point is that, like, this family, super simple one, certify this one, that at least behave somewhat like random function, right? It's in a useful way. It's not as strong as like n-wise, but it's certified this much, and it's simple. It's a simple family. A quick question, like, is this family uniform? It's not, but why? Because if you, like, let's say x is 0, then it's gonna always map to 0. Right? It's not uniform. Like a uniform function need to map everything to uniformly, like to random place. But here it just always maps x to 0. But it certifies this. Okay. Okay. So now let's try to implement what we did again, but without a completely random function. Okay. We remove this assumption, and now let's replace, let's sample H from a family that with small collision property. And you know that now, like you see some example that H can take just O1 space and takes just constant time to evaluate. Okay. And now, okay. Let me do something quick.
There's like a lake, big house.
Okay. So the algorithm was the same. And here we know that like the time to evaluate H is just all constant. Now we just need to analyze this. The size of the linked list on each cell, right? But now we can really use analysis from Ball and Binns. Why is that? Can you tell me why? Yeah.
The assumption that each time the ball is thrown into the bin, it's independent. You
Exactly.
can't use that assumption anymore.
Exactly. Yeah, like each ball in balls and bin, every ball is just independent, like go to each place randomly. That's like it behave like a completely random function. We don't have that anymore. We have something much simpler, but it's harder to analyze now. Okay. But so we need a different analysis. Okay. But we still can try to analyze it, right? And anyway, yeah. And let's try to analyze the size of the list at the position h. So okay, there's gonna be like 1 for sure because like x is there. Now let's count how many y that are not x is in this list. Okay, so I sum over all y's that is not x. Okay. And this is gonna be like this will like for each of the y that map to the same x, it will add to the size of the list. But this happens only when y map to the same place as x. Like this is basically what like this thing is like sum over y not x, the indicator that y map to same cell as x. As x. The indicator that y collide with x.
Yeah.
So that happened with this probability. But here we kind of make analysis in such a way that we can just only use small collision property. And by small collision property, we have that this is like each of this is at most 1 over m.
Yeah.
So this is at most not equal. Okay. And there are like this many y's. So this is like at most n, this is m, so this is 1. So you see like we need to like we use different like a more efficient hash family, and we just need to change the analysis so that it's like enough just for this family. Like we write the analysis so that like we can just this is enough for the family. Like this is something that we can bound using only the property that is guaranteed by the family. Okay. And so we get this. Like the space is linear and the expected time is constant. What about worst case time? Actually, we don't guarantee anything here. Okay. It can be bad. But maybe in the next homework you might see somehow how to do something about this. But okay. But what have we learned today? We learned about like some basics of probability, and you see that at least like this paradigm that we do next time tomorrow, like on Thursday too. Gonna design algorithm that assume complete random function first, and then try to replace that random function with like a more efficient one. Okay. And so we learned this today. It improves upon binary search tree. Okay. There are more efficient hashing families, like hashing scheme, but I decide not to teach you because I think there are more exciting things. But if you want to learn it, you can look at like a video lecture from the previous year. But yeah, next time we're going to talk about streaming algorithm. And let me end with this this open problem that can we do what we did but deterministically. This is still open problem that is a big one, and it's like posed by Mihai, but he unfortunately have passed away some time ago. Okay, see you on Thursday.
Thank you.